things I regret in life, it's not attending to his wedding in Chennai a long time ago. And so you'll see he will speak about some sort of flow. Thanks.
Thanks, Claudio. All right. Anyway, it's nice to be in this room where I think for some years I've been on this screen. I don't know, the Wednesday seminar. Anyway, but so I wanted to give a few talks about things related to hydrodynamic limit, which probably everybody is familiar with, but so the mathematical theory is before this paper, going back to Dobryshin and others, but this paper in particular set the stage for lots of development, and soon after, Yao gave a different way of proving hydrodynamic limits, and so the talks are based on some of the ideas and some extensions and variations of the methods used in these two works. So we're mostly considering these two works could be applied to interacting diffusions or other things like this, but we'll stick to looking at problems about jump processes which interact with each other indexed by ZD or something approximating ZD like a torus, and the types of systems where we'll be using will be exclusion processes, zero range processes, and some Glauber dynamics. Okay, and so the first two are mass conservative systems, and the Glauber one, you'll have some birth and death, and so there, in this talk, we'll be combining one of these with also this kind of dynamic. Okay, and so the three talks are so today is something about deriving mean curvature flow, which is a continuum flow on let's say if you embed it on RD, and so we'll be going from ZD to getting these flows on RD, and the second talk, I think I'll probably do large deviations. So if you follow one of the particles, it's interacting with others. How do you assess its asymptotics? What are the large deviations, for instance? And it relates. The answers involve hydrodynamic limits in some way. Okay, and then the last one will be deriving an SPDE. So the last one will be considering a hydrodynamic limit of one of these particle systems, but there's a background disorder, and so the particles have to obey this disorder, and then the limit equation that one gets is usually a PDE, but the environment will survive, and so so there's a random element to the PDE. We can call it an SPDE. Okay, and so all throughout, I'd like to point out a few open problems, and feel free to jump in, ask any questions. Okay, so let me start with the first talk. So I'll probably go back and forth if there are any questions or anything like that. So please feel free. Okay, so the first talk is about this mean curvature, derivation of mean curvature flow, and so we wrote it down. It's I think it was appeared last year. I have it here actually. So it's 2022. Okay, so and it was done with Perla El-Katani, Funaki, Hillhorst, Hyunjin Park, and so Danielle is a senior PDE person who works in reaction diffusion equations, and Perla and Hyunjin at that time were her students, so anyways, this is how it became that it became such a big group. Okay, so let's just start with a simple cartoon first. So you can think of particles or different types of particles. Maybe the pluses are you can think of spins or just plus particles, and then zeros are zero particles or something like that. Okay, so there's maybe two types of species, and maybe we can put them on the lattice like this, and so the green curve is the interface between the two species, and if the species are moving, or if a plus can become a zero and a zero can become a plus, for instance, this plus right here, it's surrounded by more zeros than it is by a plus. There may be some push for it to become a zero, and so the interface will move over time, and one of the flows of the interface is mean curvature flow, but there are other flows that you can also consider, but we'll be considering mean curvature flow in this talk. Okay, I'll mention some other flows at the end. So this is the discrete picture. The continuum picture is, maybe this will smear out to something like this picture right here in 2 dimensions. And so what is mean curvature flow? It's so at every point on the interface, if you look at the inward normal from it, then the velocity in the inward normal direction is the curvature at that point. So in this case, the curvature is negative, and so it's flowing out. And in this case, the curvature is positive and it's flowing in. Okay, and so this little n is our dimension, and so MC, how they usually write mean curvature is average over the principal curvatures. In 2 dimensions, there's only one curvature. So this n minus 1 is just 1, and this is just the curvature of the figure at the point. In 3 dimensions, you'll have, if you think of the tangent plane, there's a normal, and then there's 2 directions. Each one will have a curvature associated with it. You would divide by 2. What we'll show is that you get rid of that 2, and then it's just the sum of the principal curvatures. So that's the flow that we're going to try to derive. If you think of it as a graph, so let's say that y is equal to fxt, then df dt is equal to so this will be the if the interface is a graph in 2 dimensions, this is the equation of mean curvature for the flow. Okay, and so so this interface will move according to this PDE. Okay, and another way to think about it is if we go back to this picture. So if we inscribe the circle here, so let's say that's inscribed circle as radius r, then of course the curvature at this point is 1 over r, and so if we define a distance. So if we define the a distance, so this is distance of x where x is in the outside part. So so if your x is here, then this would be just the positive distance. And if your x is inside, it would be the negative distance. So if your x is here, then it would be the negative. And so if you look at the partial derivative of this, this is another way to describe mean curvature flow. So on the interface, D satisfies this equation. So you can see that so D is roughly, this distance is roughly like r. So D is in polar coordinates is roughly r. So the Laplacian of D is just 1 over r. So you can also understand mean curvature this way. Okay, so so this equation will come up. Sometimes you can put a velocity here, a speed parameter. Okay, so okay, so is that okay? Okay, so this is what we mean by mean curvature, and so one more point. I mean, I'm going to get to it. There'll be a later slide, but in 2 dimensions, I think you can imagine, and you already know that it's going to become like a ball and then shrink to a point. Okay, in 3 dimensions, it can pinch off, and I'll have a slide about that. Okay, and so we'll be also interested in the time to singularity, whether the time that it gets to a point or it pinches off. So I'll talk about that in a few minutes. Okay, so this problem is an old problem, okay, and of course studied in the physics literature, for ages. and also in the 90s, rigorously in different types of models, including particle systems. Bonaventura and Katsoulakis, Souganidis studied in around 95, and recently Funaki and Tsunoda also studied in the same system with a different method, which is what we're going to try to elaborate on. Okay, so I can talk a little bit about the methods of Bonaventura later on if there's interest. So this is what is known before we started this work, and so I'd like to go concentrate more on interacting particle systems, although you can see that the phenomenon also holds in other models. Okay, so what's Kawasaki-Glauber? I think many of you know this already, but Kawasaki just means that neighboring sites will exchange their values at rate 1. Okay, and Glauber means that at some rate, which depends on the configuration, plus can become 0 and 0 can become plus. Okay, so this is the unscaled picture. Okay, and we're going to be considering, because the previous one, the Kawasaki is symmetric. It's natural to consider diffusive scaling for the Kawasaki part, and so if we coarse grain the lattice so that the bond width is 1 over n, then if we make that our if we do this first, then diffusive scaling would be speeding up at time would be sped up at n squared. Okay, and similarly, the Glauber part will be scaled at some rate. Let's call it k. We'll let it depend on n later on. Typically, k should be smaller than n squared. Okay, so it's exploring in the Kawasaki system. It's exploring more in a faster way than the reaction part, which is the Glauber dynamics. Okay, so having mentioned the Kawasaki-Glauber setup, part of our interest was just to see how some of the arguments, or if there's new arguments needed for other interactions. So if we make the interaction, the exploration model something different than Kawasaki, maybe so-called zero range, I'll mention that in just a second, what it is, then what changes? Okay, and so there will be a reason why we stick to dimensions higher than 2. I can tell you right off, in dimension 1, there's no motion of the interface. I'll get to that. Okay, and so part of the reason also to consider other exploration mechanisms is that maybe the answer you see in the Kawasaki-Glauber is this speed parameter is always 1, but it turns out that in this system, this lambda naught will depend on the microscopic jump rates of the zero range process. Okay, and so this is basically following relative entropy methods, which is how Funaki and Tsunoda did it for the Kawasaki-Glauber system. And there's some twists and new things along the way. Okay, so So what's the zero-range Glauber? Zero-range process is so these are all informal things. I'll state things more formally in just a second. So zero-range now allows more occupancy. So the number of particles at a location doesn't have a bound. So for instance, in this location, there are 3 particles. So what happens is that each site has a clock. The clock rings with a rate which is a function of the number of particles on that site. So let's call the function as g. So once the clock rings, then you choose uniformly one of the 3 particles to jump. Okay, and so each particle is jumping with this rate, and we'll just stick to the case where once it chooses to jump, it jumps symmetrically to nearest neighbors. Okay, so if you're unfamiliar with this process, then a case of the zero-range process is the case of independent random walks. So if the function g of the number of particles is actually just linear, j, then you can also interpret every particle having an exponential 1 clock, and then the minimum of the 3 particles, which one is the minimum is the one that moves. Okay, so here's the informal statement of the results. Okay, so we're going to choose the Glauber rates, the rates of putting pluses and the rates of taking away particles, so that there are 2 densities, let's call it A1 and A2, which are stable. Okay, so just bear with me if it's not completely clear. So if the system in a particular region has particle density A2, then it doesn't really move as much. Okay, and similarly for A1. And so let's say this is your initial condition. So this is your continuum initial condition. So so my cartoon, this could be like 2-dimensional space down here. And so this is our continuum density profile initially. Okay, and so if we look at the level set corresponding to A star will also be an equilibrium point for these Glauber rates, but it's an unstable one. So if you look at the level set corresponding to that, so in space, this part and then this part, so the boundaries of those, that will be what we call gamma naught. And so inside, the density is higher than it is outside the interface. And so what's going to happen is that over time, having chosen c plus x and c minus x carefully, you're going to get a step function. And the interface itself will move according to mean curvature, so that inside it, it'll be all A2, and outside it, it'll be all A1. Okay, so that's informally what we're trying to show. Okay, and so we're gonna formulate it as a hydrodynamic limit, and so anyway, this is what I just said here. So if you focus on the level set of A star, it's evolving. It turns out it will evolve by a certain mean curvature with a speed reflective of the zero range parameter g, and also the Glauber parameters c plus and minus, and the convergence to the step function will formulate that as a hydrodynamic limit. Okay, so we're going to try to do this in one step, but there is a direct step or a direct approach, but there is a way to see what we're going to derive through 2 steps, which is already present in the literature. So for instance, if you fix the Glauber rate, the Glauber scaling. So we're going to scale Glauber rates by k, but let's just fix k. Right? So the only thing that's being scaled is the exploration part, the zero-range process, or the Kawasaki process. Okay, so then in that case, then you have a reaction diffusion particle system. You will then converge to a reaction diffusion continuum PDE. Okay, and so this was done in the 80s, Demasi, Ferrari, Leibowitz, and Mustafa Meraghi did it in the 90s for the zero range plus Glauber. Okay, so in particular, so by a hydrodynamic limit, I've kind of said this without really defining it. So we're looking at the evolution of the mass distribution in the system, and so this is so if G is indicator function of a set, then this is the average number of particles in that scaled set at this scaled time, and so these numbers are converging to something, and they're converging, let's say, to this density U, which depends on macroscopic time t and macroscopic time x. And so this convergence, there's many types of hydrodynamic limits. This is one of them where you could do it for each time t. This is a random variable. This will converge in probability to this. So it's a law of large numbers. Okay, and there are other versions where you could also integrate over time and then do all sorts of things. Okay, so weaker versions. Okay, and so for the Kawasaki Glauber system, this is the equation that the density U will satisfy. That's what was proved by Demasi, Ferrari, and Persuti, and Meraghi was proving this. So here you get a nonlinear reaction diffusion equation. The function phi has something to do with this G. Okay, so it's some phi you can think of as the expected jump rate. Okay, and this function f, which is in both of them, is expected rate in minus rate out. Okay, C plus is rate in, C minus is rate out, and you're taking average with respect to a measure nu rho, which I'll define later. It'll be the invariant measure for the Kawasaki system. It's just Bernoulli product measure. In the zero-range case, it'll be something which is invariant to the zero-range exploration process. Okay, so step one is this. Okay, so you have this hydrodynamic limit. You haven't scaled k, and now step two is it's just purely a PDE question. You have these this PDE which depends on k. So now the game is to let k go to infinity now, and then see what you get. And so this is So this is in the Ferrari Demasi Persuti equation is this equation, which is sometimes called an Allen-Kahn equation. And when this f, so at the moment this f could be anything. Okay, so it could be, it didn't depend on the. I didn't really put too many conditions on C plus or C minus. It's just rate in minus average rate in minus rate out. But if you now also insist that this f is, let's say, the negative derivative of a balanced double well potential, something like this. So let's say V is something like this, where you have two equal wells. Okay, and so negative, the gradient of this will be this function f, which looks like this, and you see it has 3 zeros. And so these will be the stable points. This is unstable. Okay, and so so this is the system that you can look at, and so what happens is that they show that the solutions of this equation as k goes to infinity converges to exactly what we want, the step function with one density inside the interface, another density outside the interface, and the interface will evolve by mean curvature. Okay, so this is a
This is known in some special cases.
this is known as long as you know, certainly if you satisfy this balanced this condition right here, then that will force mean curvature. If you, for instance, if you're unbalanced, suppose that you have two wells, but maybe this well is higher than this well, then what it turns out is that you'll get a Huygens flow.
Yeah, but until the time of singularity, say it's rigorous this time.
That's right. Yeah. So it's so that's a good question. So it's rigorous up to the time of singularity, which I'm going to come to in just a second. But there is there's the work of Katsoulakis Tsoukanidis can extend it past that. In the geometry literature, they call it Brocchi's flow. So after the singularity, what happens? So it could be that you have non-uniqueness in how you can extend. There are specifications to get a unique extension, and that extension is due to Brocchi, and they're able to get past the singularity. But we will always stay before the singularity. So I agree. Most results are rigorous up before the singularity. There are a few rigorous results. Yeah. Yeah. After there are a few works though which do it after the time. Okay, so in our situation we have this equation, and so what conditions should we put on f? You know, now you have this. You know, it's not Laplacian U; it's this nonlinear Laplacian. Okay, and so you know, as a guide, you can think of f as f of phi inverse applied to phi of u, and then do something. And it turns out that that the condition that we should put on f is that this integral is 0. So in the case when phi of u is equal to u, this just reduces to the integral of f from one stable point to the other, which is definitely 0, because f is the minus gradient of something. And the gradient at the 2 points are the same. I mean, v at the same 2 points are the same. So so this is the so we call this the modified bistable condition, or that we should impose, and it's derived from. I'll have some words about that. Okay, so this is the condition we should put, and so with that specification, then what's going on in the PDE picture? So we're going to take this as what we're going to say is the yeah. So you know, we're still talking about PDE. So I want to just motivate what the answer is. So if you take this PDE for short times, this is not as significant as the reaction term. So if you scale time, let's say k tau, then for short times, the reaction part is the dominant part of that equation, and so things are already aligning themselves so that outside a certain interface, it's one density, inside it's another, there will be some boundary around the interface for fixed k, which you can imagine that since we're scaling by k, then the time the exploration distance is 1 over square root of k. And so this is the width of the interface. This is where the action is happening. Here it's roughly close to A1. Here it's close to A2. And so this is going to shrink as k grows. And then this green curve will also evolve. So if you just do some formal asymptotics, which can be made rigorous, so if you say that the solution, the density has this kind of asymptotics in k, relative to distance from this interface, then and if you stick that back into the hydrodynamic equation, you'll get an equation for m naught and also an equation for m1, which will depend on m naught. You can solve them. Solvability is in some sense that's also another way to understand this condition. So you can actually solve for those things with this condition, and it turns out that the key thing is to understand what the flow is to understand how the distance is evolving at the interface. And so one will get that you'll get this equation, which is what we were saying is mean curvature flow, and we can also solve for this constant lambda naught. So this is the expression in terms of the parameters. So that's the two-step procedure. So the first step was hydrodynamic limit. From this, one can do the PDE limit and get mean curvature flow also. Okay, so singularities, we've already talked about it a little bit. So here's a picture in 3 dimensions. So I think we can all understand that maybe here it's moving faster down, and so in a finite time it'll pinch off. And and then after it pinches off, of course, it keeps evolving, right? But and that in this picture, I think the Brock's flow extension is unique, but there are pictures that are more difficult to draw where it's non-unique. Okay, but so we'll be doing things up to the time of singularity. Let's call it capital T. So we'll stop before this. Okay, and I wanted to mention dimension 1, which is actually very interesting. You would think it's the most natural problem to initially start with, right? So you have this is your initial density, right? And so here's a star. So these are. So that's your interface. Okay, and so the results of what we're doing actually apply even in dimension 1. But these points will never move. So eventually you'll get step functions like that. Okay, but the points won't ever move. So it's kind of strange to say it, but a point, what is the curvature of a point? So anyway, but of course, if you observe it, apparently if you observe it for a long time, then it will move. And so this is a nice question. So in the PDE literature, from the point of view of the one-dimensional hydrodynamic equation with the k in it, if you would look at very long times, then these points are moving. Okay, but this is not what we're we're not looking at such a long time. So our times that we're looking at our scaling is not suitable for this problem. It's there's some surface tension equilibrium there. I'm not. I have to remember what that is. I don't know. Okay, but there is possible motion at this scale. Okay, so okay, so let's get to the formal definitions. So these are all we're going to be working on a torus, one of these toruses, n-dimensional torus, little n-dimensional torus, and so the generator of the process where you superimpose zero range and Glauber is this. We're going to speed. So this is the formal generator for the zero range process. Here it is for the Glauber one. So the notation is e to xy means that you move a particle from x to y, and this is the rate of that happening, and this notation means that you add a particle at x, and here you take away a particle at x. Okay, so the invariant measure for the system together is there is a unique one because of irreducibility on the torus. Okay, it's a countable state Markov chain. So, but it's not explicit. It's not a nice object. On the other hand, if the dynamics were just zero range or Kawasaki alone, of course there are many invariant measures. This is mass conservative, so there should be many invariant measures indexed by density. So you would have something like this. You would have a product. It turns out that you have a product measure where the marginal is explicit. For Kawasaki, the marginal is just a Bernoulli random variable with probability rho of putting a particle, probability 1 minus rho of not putting a particle. And for zero range, it's Poisson-like. So it's okay, so this phi is a parameter where you choose it so that the mean equals rho. So anyway, so in the independent case, g of 1 is 1, g of k is k, then this is exactly just the Poisson measures. Okay, so this is very explicit, and so it allows a lot of analysis. Okay, so the function g, we should put some conditions on that. We can improve this, but anyway, let's just take it like this. So g is between two slopes. So you have one slope here, so g will be something like this. And I didn't mention one more thing. I mean, it should be almost increasing. So g of k plus b 0 minus g of k. Okay, so if this is true for all k, so B naught is like 5 or 6 or something like this. And so, you could, so it's eventually increasing. Okay, and so this is a technical condition which allows a spectral gap for the system to hold. And the Glauber rates should be bounded in a, it's a little bit more technical than just simply being bounded. They have to be, if you multiply by g or divide by g, it should be bounded, something like this. Okay, and then this function, this is an important one. This should be bistable in the sense that we gave before. Okay, and you might think this is a lot of assumptions, but you can actually construct a g and Glauber rates so that everything is satisfied. Okay, so the spectral gap assumption is useful. So if you just have so if you have L sites, so let's just do dimension 1, right? So then if you would consider the zero range system on a finite number of lattice points, let's say L of them, okay, and so jumps out are not allowed. So if your particle is here, they could only go inside. So it's so this is zero range process on this finite system. Well, it may have a spectral gap. So the generator for this system, 0 will be obviously an eigenvalue, but the next one will be, so let's do minus L. So 0 is an eigenvalue, and then the next one will be some gamma, which is positive. Okay, so so the spectral gap result that we need is that this gamma depends on L. It's something like L to the minus 2. So this is exactly the spectral gap of a single random walk on this interval, for instance. Okay, so so something like this. So in fact, it doesn't have to be exactly minus 2. It should be some power. But under this assumption, it turns out that it's minus 2. Okay, so this is what I mean by this spectral gap thing. Okay, so so the main idea to relate the to get the continuum evolution. So we're going to try to do this now directly. So we've discussed now the two-step approach, which is you get the hydrodynamic limit with k fixed, then you do PD analysis on the hydrodynamic equation as k grows. Okay, so we're going to try to do it in one step by letting k also depend on n, and it's by this relative entropy ideas. So so here are the particle numbers in this zero range plus Glauber or Kawasaki plus Glauber system. So these are random, but we're going to try to show that they're well approximated by their, the means of these will be relatively well approximated by these deterministic numbers. Let's call them means. Okay, so in some sense, the mean of this random variable is this quantity here. Okay, and so these means are linked, just like in the PDE evolution. They're going to be linked. And so we haven't gone to the PDE yet, and so this is just a system of ODEs indexed by the lattice. So it's a coupled system of you can call it a discrete PDE or a coupled system of ODEs. Okay, and so it looks exactly like the hydrodynamic equation that we're going to try to get, but k here is, k will now depend on n as we're scaling everything else. Okay, so this is the main idea here. So the random particle numbers will be close to something which looks like the discrete PDE, looks like the continuum PDE discretized. Okay, so if we can show that, then presumably, so if we can show that the random ones are close to this, then presumably the PDE stuff that we did before will get that this is close to the step function where the interface evolves by mean curvature. Okay, so what are the initial conditions? So in that picture, we should take that the initial mass density profile is smooth enough, and let's say it's bounded away from 0 and also above. Okay, and so that's this picture that we drew before. So this is our U initial picture. So this is relatively smooth, and so in particular this interface, that the level set of A star is well defined. Okay, and let's say that we're going to put particle numbers. So these will be the means of the initial random thing that we put down. Let's just take it to be one of these so-called local equilibriums where you're also having a product measure, but you put it where at x you put a random number of particles with that mean. Okay, so our usual thing if in this business. Okay, and so this is varying over space, and so this is not the invariant measure. It's a so-called local equilibrium measure. Okay, so let me now define this mu nt. This is the distribution of the process. So mu nt will be the distribution of these particle numbers. Okay, they've all mixed up from the initial condition. Okay, and but we want to say that that things are close to these. So one way to say that is to say that mu nt is close to this product measure where you look the mean of this marginal is the deterministic mean that we're trying to approximate. So this closeness between random particle numbers and this system of deterministic means, which are linked by this discrete PDE, is one way to say that they're close, is to say that the measure of the random particle numbers is close to this product measure. So you're asserting that marginally the means are the right thing, and also that it's not that far from being independent. Okay, so this is what we're going to try to prove, where k is selected appropriately as in terms of n, and this may seem large, okay, but this is actually quite small because you have the entropy inequality. So here's the measure of a set A. Let's take this set A in particular. This is the one that we're really interested in, right? So this is the average number of particles, and this is the average number of particles with respect average of the means. So if we can show that this random average is close to this deterministic average, then we're done, at least with respect to result 1. Okay, and so so if we could consider this as our set of configurations where this is this difference is not is big, then the use of the entropy inequality gives you this. Are we okay with that? K is going to be it's going to be log of n to a power. Okay. Okay. So anyway, so what you get here is that so you see that this if we show that this is of this order, then the denominator, remember nu t is product measure, so this is we can estimate the probability of this event with respect to the product measure very nicely. It's just a large deviation calculation, so this will be like e to the minus constant n to the power n to the dimension. So when you take log of it, you'll just get order n to the little n, but the top is order n to the n minus epsilon, so it goes away. Okay, and then the second part is to analyze the discrete PDE, so there's no probability in this part. It's it goes along the PDE ideas we mentioned. Okay, and so this W is the step function where it's A1 outside, A2 or A2 outside, A1 inside, and interface moves by mean curvature. Okay, so so putting that together, this is the result. Okay, so what's Kn? That's the question, right? So it comes out through analysis, some Gronwall analysis. Okay, so Kn is whatever you need in order to get this result. So so there's some freedom in choosing what K is. So the first thing we do is we differentiate the relative entropy, and this is an inequality which is implicit and maybe even explicit in Yao's paper. But definitely it's present in Milton's paper with Ottavio. Okay, so it's a little complicated here, but everything is well defined, and it turns out that for what we're going to do, we don't, since we're looking at hydrodynamic limit, which is the law of large numbers, we can afford actually not to work with this term, which is always negative. So we'll try to just we'll try to bound just this term here, which is of uncertain sign, and so our goal is to bound this by something involving k is in the problem, right? So this is the estimate that we'll try to show. The sigma is not a friendly object. It's something that comes and is determined by this Nash bound. Remember, U is satisfying this discrete PDE. Okay, and so this is a quasi-linear discrete equation. Okay, and so Nash inequality is used to analyze it. And this is the statement of Nash inequality. Okay, and this sigma is coming out in the argument of Nash inequality. Okay, so it's something between 0 and 1. And so this is the result that we're able to prove. So with this result, so let's just, so we could have started from something which was not exactly local equilibrium, but if we start from the local equilibrium, then these two things are the same, and so this is just 0, so it's easier. So if you just look at this from Grunwald's inequality, so you have the derivative of relative entropy, or rather, so we've integrated in time, so the relative entropy is less than this. So then this gives you this from the Grunwald inequality, and k has to be less than this guy. So it's coming out from the Grunwald inequality. Okay, and
anything slower will do.
Anything slower will do, but it should go to infinity. Okay, so I should mention in the work in the 90s for Kawasaki, Glauber by the Italian school Bonaventura, who was a student of Presutti, they were able to do it where k is a small power of n to a small power. Okay, but even that was not optimal because I think k can be anything which is little o of n squared. Okay, so if you like calculations, then one can calculate this quantity. Okay, so it looks like this is a little bit long, involved expression. Okay, but so you see you have all these nonlinear functions of the configuration. In the Kawasaki Glauber situation, what you'll get are polynomials in the occupation variables, and one can get very nice estimates using this this Dirichlet form, which are better than what we can get. Okay, but in the nonlinear situation, it's not obvious how to use the Dirichlet form yet to do something better. Okay, so the idea is to linearize. So in this previous equation, this g should be close to its average, which is phi. C plus should be close to its average, which is the expected value with respect to this invariant measure of the zero range process. And so if you could linearize, then we can do some cancellations. So here's this is the main estimate. So you have a function h. So this is the mean value of h. And this is, let's say, the next order term. So there's a prime here. So this is h. So the derivative of this function. And so in some sense, this is a linearization estimate. And so this is what we're able to prove here. Okay, so if you accept this, and you go back and you replace everything in this expression, okay, everything in this expression by the linear things, then by the form of the discrete PDE, all the terms multiplying e to x will go away. And what's left are the next order corrections. So this is, so the next order things are exactly this. So, you can see entropy inequalities. This is expected value with respect to the measure mu n, which is the distribution of the particle numbers. So it's a non-stationary estimate. And so we're using relative entropy here. And then we're getting, with the entropy inequality, there's some things that we have to do. Okay, so this this epsilon, which is here, I guess, one can calculate that. It's not optimal, but this is what it is. And so just rough notion, how do you do this? So the idea is you approximate this by its conditional expectation given the average particle numbers in a certain mesoscopic box. So something like that. So here L will be a small power of n. Okay, so if we can do that, then the next step is this average. Remember, the dot 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 is a linearization, right? So if you think of Taylor expansion, the next order term will be something involving quadratic things. So so one might think that this is whatever is you're taking conditional expectation of a linearization with respect to average number. So it should be something like the next order term would be average number squared. So this is just Taylor expansion intuition. Okay, and all of these things have to be made precise. Okay, and so this is where so in this first part we use so to get that this is well approximated by this, we're using the spectral gap stuff. Okay, and then in this part, this is local central limit theorem. Okay, so so I thought maybe I would just mention a few avenues just for fun. But I can go through more of the proof. Probably you're a bit tired now, but if you like, or are there any questions before I discuss some of these extensions and things like this? Okay, so let's try a few extensions. Okay, so let's see here. So the so mean curvature flow was actually used to derive the KPZ equation. I think people know that, but it might be fun just to remember it. So KPZ equation. So you have let's say that y is. So you have something like this, right? So the same picture that I drew before. Okay, and so let's say that the inward normal is equal to mean curvature plus a deterministic velocity a. So this is also an open question, by the way. So we just derived in some sense interface following mean curvature, and I mentioned that if you had unbalanced well, then the interface will flow with a certain velocity a. So that's Huygens flow. Okay, and so this is a1, this is a2, so it'll be a1 here and then a2 here. So a2 is being driven out. Okay, so one can actually derive this. Also, this is we did this recently, but we haven't put them together yet, by the way. So that's an open question. Probably one could do it maybe by choosing a2 and a1. Maybe they're within each other by 1 over n or something like this. There may be some way to do that. The problem is to derive mean curvature, derive interface flow where you flow with that so at the interface the inward velocity is moving curvature plus a. So the curvature at this point, but plus a deterministic piece. So there's a growth, but there's also some variation.
This is what's expected if you have a double well potential.
No, if you have double well potential, then you only move with each point is moving out in the normal direction with speed, which is something to do with the difference of the minimum.
So what's the microscopic model behind K plus A?
So it's open question, but I was thinking one could choose the Glauber rates so that A2 minus A1 is maybe order 1 over n to some power. So so we have f of rho is expected value c plus minus c minus. And this f is supposed to be the negative gradient of this function. Choose c plus and c minus so that the zeros of this function are not so far apart from each other. But there is a difference. So maybe one could get, just like when we, in hydrodynamic, when we plus constant times gradient, we can get this or yeah. So we can get this by just doing 1/2 plus 1 over n. So you consider the weakly asymmetric system, and then we can get this hydrodynamic equation in diffusive scale. So I'm thinking that maybe one could get this together, possibly by choosing the rates carefully so that it's almost a balanced well. Okay, but that there may be some problems. It hasn't been done. I don't think it's been done. Okay, but anyway, with the KBZ equation, here's the equation for okay, so this will be the equation for this interface if you follow this. So at this point, you're moving up with this speed. Okay, and so this is in the KBZ paper, and so if you assume that gradient of f is very small, right, and then you linearize around f minus at. Then you're getting KPZ equation. Plus okay, and then they said, well, let's when we were linearizing, there's always a little bit of noise in the system, and so then they added on this space-time white noise. Okay, so that's the challenge to actually rigorously get the KBZ equation from something like this. Okay, that's one problem. Volume preserving flows. Okay, so let's do that. Okay, so this is so if you have a volume preserving flow, then so you have a balloon with water. It's not it's going to evolve, but it's not shrinking, right? So so this is so this goes under the name Healy-Shaw flow or Mullins-Serkirka flow, and so so what's going on? So is in terms of the PDE. So you have something like this. Okay, so you have a fourth order equation. So this is what's called a Hilliard equation. So as epsilon goes to 0, then you can look at the solutions, what they do, and they converge to something like this. So m epsilon goes to u, where so this is the specification of these two things. So this is basically Laplacian. So it's going to converge to something where inside you get Laplacian of one phase is 0, and outside is also 0. On the boundary, it's equal to the curvature, and the boundary gamma t is evolving difference of normal jumps. Okay, and so this is even to understand this takes a bit of time. So so this from here to here, this has been proved in a few papers, and I just mentioned that. So from microscopic system where you have more than one conservation law, right? In all the systems that we were looking at, we had implicitly one conservation law, mass, right? So they were able to derive this as the hydrodynamic equation. Okay, and so so a problem would be to these are all hard problems to go directly. So epsilon will be something scaled in n.
Okay, now the PD part, I don't think it's really known to the last bit, this convergence, no?
It's known in a few papers. There's Bates and co-authors.
I don't know most updated results, but like 10, 15 years ago, was a state of the art on this, but they had some, so they, as I remember, it was written slightly different, but they had convergent up until the first singularity, but not the first singularity of the limit of u, but the first singularity of the limit of m epsilon, which of course nobody knows when it is.
I see.
You have a limit, and if it's not singular, it coincides with it. I think it's something like this.
I looked at a few papers before coming, but this is definitely a harder problem than mean curvature. So so less people are working on this kind of stuff.
I'm not sure if I explained myself. Like I think 10 years ago, the results they had is like every sun converges to something. If until the time this limit is known on some sequences, until the time that this limit is non-singular, it coincides with the u there.
I see.
Until the, but you will never know, even if the initial condition for u are good, if the limit of m epsilon will be non-singular until some strictly positive time. I don't know if I explained myself.
No. I appreciated it. I am not an expert at this problem yet, but I think people are still working on this, and there's even some very recent papers. So I think there's something worth looking into if you're interested. Okay, and maybe the last thing I'll say is, improving K. I didn't talk about the method of Bonaventura. It's using this correlation methods. Okay, maybe I'll skip that. So maybe I'll go to the last one, which is more phases, which is again one of these, kind of open problems. Okay, so you could have A1, A2, A3. So even the physics of how a system like this evolves, in this region, it might evolve by mean curvature. Okay, but around the point where all three come together, there's lots of unknown things, so understanding anything in this region, I think, would be of interest. Okay, so maybe I can stop here.
Well, thanks a lot. Any further questions? So if not, we continue on Thursday.
Thursday. So